Hello everyone, in this video we're going to discuss how we can use Newton's second law for rotational motion. And so what this is saying is we have the acceleration, or angular acceleration, is equal to the sum of the torques over the rotational inertia, or the torque of the system over the rotational inertia of the system. And so I rewrote this just by multiplying the I to the other side. We have this torque equals I times A. And we can kind of think of this as a force equals the mass times the acceleration. And then, so we can actually use the second law to derive this equation. So let's do that. So we know force equals mass times acceleration. And when we say this, when we say acceleration, we're always talking about this tangential acceleration because we're moving in some linear motion. And so we know the tangential acceleration is just equal to r times alpha, or the angular acceleration. And so now we can plug that in and we get force equals the mass times the radius times this angular acceleration. And now what I'm going to do is just multiply this whole equation by r. And so we can always multiply both sides by some variable. So now we have r times f equals mr squared alpha. But now you may be noticing here, we have r times f, that just equals the torque. Mr squared just equals this rotational inertia, and then we obviously just have alpha, the angular acceleration. So now we have this equation, which we just derived from the Newton's second law. So pretty cool, we can easily derive it. And so really all these things are just related through radius. Radius is the big relator. And I had a video talking about how you can translate between each one of these different accelerations and velocities using radius. So yeah, this radius is very important when we want to kind of convert from linear to rotational. Alright, so let's do an example to see how we can apply this equation. Okay, so we have a 10-meter rod is released from rest and rotates about frictionless pivot as shown below. What is the angular acceleration right after the rod is released? Okay, so first of all, we need to figure out what's even going to cause this angular acceleration. Well, we obviously have some torque here because this rod is held up by nothing right now. So at this center of mass, there is some force due to gravity, right? And so this rod is going to, when it's released, is going to swing around like this. Okay? And so in a previous video, we actually derived what this rotational inertia is. And so you would either be given this or be given the center of mass rotation, then have to derive this. But for this question, I'll just give the rotational inertia, which equals 1/3 ml squared. And so that's the rotational inertia of a rod rotating about its end, because it's rotating around the end of the rod, not through the middle. So yeah, you would have to be given this or given something so that you could derive it. And if you want to see how we derive this, in a previous video where we talked about rotational inertia, we used the parallel axis theorem and derived it. It was pretty cool. So go back and watch that later if you want to see how we derive this, but for now it's just given. And so we need to figure out how we can find the angular acceleration. So we know that the angular acceleration equals the inertia over torque. So I'll just go ahead and write it in the kind of form that we are most familiar with, as the torque equals I times the angular acceleration. And so let's see, we know the length of the rod equals 10 meters, right? And that's really all we're given here. We obviously know I, and so we need to figure out how are we going to find this. So we know the torque is going to be the force due to gravity is what's causing the torque. So this is a gravitational torque because there's nothing else, no other forces are applied to this rod when it's released, times the radius. And so what is the radius going to be? Well, it's obviously applied right in the middle because we're assuming this is like uniform beam or rod. So the radius is just going to be 1/2 the length. And another thing you might be thinking here, this is going to rotate in this counterclockwise direction, or no, this clockwise direction, which by convention, we're going to call the negative direction. So this should actually be a negative torque, and so we'll have a negative force due to gravity 1/2 L. Okay? And then the rotational inertia we were given as 1/3 mass of the rod, length of the rod squared, and then this angular acceleration, which is what we want to find. And so we have this mass, we don't really know what to do with it, we weren't given the mass. Well, we know force due to gravity is on this other side, and force due to gravity just equals the mass of the beam times gravity, and we still have this 1/2 L equals 1/3 mass L squared alpha. And so now these masses cancel, and also one of these lengths will cancel. And so now if we simplify this a little bit, we can say that negative 1/2 of gravity equals 1/3 L alpha. Okay? And so now if we divide over this piece, we can get, I'll write it over here so I have some space, alpha equals negative 3g over 2L. And now we know what the length is, that's the only thing it really gave us, and we know gravity obviously. So we can now plug in these values here, which is, okay, and then 2 times length, which is 10. And so we get a negative 1.47 radians per second squared. And so what does this negative mean? Well, simply just the direction of rotation. So the acceleration is also in this negative direction. So we could also write this as the angular acceleration is equal to 1.47 radians per second squared clockwise. And that has the direction. Since these are vectors, we do need the direction, and so that will be our final answer. Okay? And so now you might be thinking, does it matter when we're calculating this? Is this angular acceleration constant? And the answer is no, it's not constant. And let's see why. So let's consider the rod has rotated and now it's at this bottom position as shown here. So it started up here, this was the rod, and it swung down and now it's in this position. Well, now we know the rotational inertia is still going to be 1/3 mr squared, nothing changed there. The length is still 10 meters. But now we need to find what torque we're going to be using. We still have this Fg like this, right? And so if we write out our equation, we still have the torque equals the I times the alpha times angular acceleration. So I did actually mention last time, but we used the force due to gravity times R equals I times alpha. But I didn't mention the torque, of course, needs to be multiplied by sine of theta. But in this first case, we had an angle of 90 degrees right here. So sine of theta is just going to equal 1. So we don't even need it if it's perpendicular. But in this case, our theta that this angle is making to the rotation is 180 degrees. And so if we take sine of 180, force times gravity, R equals I times angular acceleration, this just goes to 0, so everything is going to go to 0. So if this equals 0, this whole side equals 0, and we know the rotational inertia doesn't equal 0 because it equals this. The radius is going to be positive, the mass is going to be positive, so this does not equal 0. So that means this alpha, this angular acceleration, must equal 0. And so that's why it's changing. So as this rod rotates down, it's losing acceleration as it gets down to here. And once it hits here, the angular acceleration equals 0. And now let's say the rod is up here. Now this angular acceleration is going to be in the opposite direction because the rod's going to start slowing down. And this angular acceleration is actually going to be positive since we defined it as negative originally. It's a negative value. It's now going to be positive because it's going in the counterclockwise direction. So it's important to note that the angular acceleration in this case isn't going to be constant because the torque is changing this angle. and which makes sense because if it was constant, it would just start swinging around this pivot at a constant rate. But we know that doesn't happen, obviously, if you were to drop it, because gravity is now going to be affecting it in the opposite direction in terms of rotation, even though the force due to gravity is obviously not changing its direction. Just where it is relative to the pivot changes, and that's why your angular acceleration is going to change. And so that's why it's 0 in this case. Okay, so that's about rotation. That's all we have for Unit 5 of kind of introducing this rotational motion. And in Unit 6, we start talking about like energy of rotational motions and how that applies. So that's some exciting stuff. So make sure you stick around for that. Leave your questions in the comments for anything about this. And I hope to see you in the next one.